All right, good morning, class. Hope you're having a nice Friday. I'm not here, so we're going to have a video to watch. It's probably going to be pretty long, and I apologize for that. If my dogs bark, I'm also sorry for that. Okay? And so we're working on 2.8. This is the end of chapter 2. And so make sure you're taking notes. I'll ask you to pause and try things like we do in class. The more intention that you put into this, the more you'll get out of it. I know it's not the same as me being up there yelling at you, but the harder you work, the more effective this is going to be. And so feel free to pause me and write at your own speed, do your stuff. Just make sure you're paying attention. Don't bother Miss Bondi. She took her time to sub for us, and that was really nice of her. So we're looking at function operations and composition. Function composition is so cool. I genuinely enjoy this. And so our essential question for the day is, how do we perform? See, here's my dogs barking. How do we perform function operations? And compose functions. And so this term right here is going to be relatively new to you. We don't know what composing functions means, but it's fairly intuitive, and we will see how it works pretty quickly. Okay? So there are operations on functions, just like numbers, right? When we look at two numbers like 5 and 6, we have operations that we can do with those numbers, right? We're allowed to add those numbers together. We can subtract those numbers. We can multiply those numbers. We can divide those numbers. Those are very standard, right? And these operations are actually more than just on numbers. We can do operations on all kinds of algebraic structures, especially functions. So what we're saying here is, given two functions a and b, or f and g in this case, sorry, I don't know why I said a and b. So given two functions f and g, for all values of x for which both f of x and g of x are defined, right? So for every member of its domain, the functions f plus g, f minus g, f times g, and f divided by g are all defined as follows. And so these are different functions that have names. So the first one is called the sum function. That's right here. And sum, of course, means add. So it is the function of f plus g, which is literally just take the first function and add it to the second function. Add the functions together. That's the sum function. Works exactly as you would expect, right? The next one is f minus g. That is the first function minus the second function. A little bit more dangerous, of course, because subtraction symbols cause us some issues, but definitely an effective function. The third function is the product function. It's fg of x, which of course is just f of x times g of x. These work all exactly like you'd expect. And the last one is f over g of x, which is just the first function f divided by the second function g. Pretty standard stuff. Works the exact way that you would expect. The domains of these functions are all real numbers that are in the intersection, and we've talked about this, the intersection of the domains of f and g. While the domain of f over g includes all the ones in the intersection, except for when g is 0, because of course you cannot divide by 0. Now, just a brief reminder of what intersection might be. Remember, if we had two sets like this, so here's our first two sets. So here's set A, and here's set B. Say we had 1, 2, and 3, and 4, 5. I'm going to put a 3 back in here. I'm really sorry. And so if we're looking at the difference in union versus intersection, right? So this first one is union, and the second one is the intersection. That's a big word to write here. Intersection. Okay. When we look at A union B, that's going to be all the numbers that occur in either set. In this case, 1, 2, 3, 4, and 5. Right? If the number occurs somewhere, that's great. But today we're talking about the intersection. The intersection, this one right here, the one that we're interested in, I want to use the highlighter right here, that one. One that we're interested in is all the numbers that occur in exactly both. In this case, it's just the number 3 that's in both sets. And so what this does to us is it causes our domain to be the more restrictive of the two different domains. the function that is more restrictive, like for example, if our domain is 0 to infinity, that's going to take precedence over the negative infinity to infinity. So this is going to cause it to be more restrictive. But at the end of the day, we can look at the functions that we create and find the domain from there. So let's practice with this before we get too far in here. So here we have some examples of us just evaluating functions. Now this is no different than, for example, saying, what is f of 3, right? That's evaluating the function at negative 3. What we're actually doing is just evaluating these functions, but they're going to be the sum, difference, product, and quotient functions. So here we have f plus g, but evaluated at 0. And so this is like shortcut mode. So of course f plus g of 0 is the same thing by definition as f of 0 plus g of 0, right? That's what the definition on the top of the page says. Now f of 0, of course, is just 0 plugged into the f function. So 3 times 0 minus 4, that's negative 4. G of 0 is just 0 plugged into the g function. So 2 times 0 squared is 0 minus 1, so that's negative 1. So I have negative 4 plus a negative 1, so of course that is negative 5. So this is our solution right here for the first one. Now at this point, it's probably worth your time to pause me and go ahead and try B, C, and D. This is something that you can definitely do. This is just the standard run-of-the-mill plug and chug, okay? Pause me, resume me when you're done. Okay, hopefully you're done. So here we have f minus g. That by definition is f of 4, and of course it's minus g of 4, and we're just going to shove 4 into both f and g. So we have 3 times 4, and I'm doing a lot of this in my head. Feel free to write the steps if you want to. But 3 times 4 is 12, minus 4 is 8, so f of 4 is 8. G of 4 is 32 minus 1, 31. So I have 8 minus 31, which is a negative 23. Enjoy me thinking I didn't bring a calculator. I'm just doing this in my head for now. Hopefully I don't need one. Okay, and that is our final answer in this case. F times g of negative 2. Again, I'm plugging these into the f and g functions. So this is the same thing as f of negative 2 times g of negative 2. F of negative 2 is just 3 times negative 2 minus 4 is negative 10 times g of negative 2 is going to be 8 minus 1, so 7. So negative 10 times 7 is just a negative 70, and that would be our final answer in this case. That's what box I made for us there. And then, of course, f divided by g is just going to be f of 3 divided by g of 3. F of 3 is just 3 plugged in, which is 9 minus 4 is 5. And g of 3 is 9 times 2 is 18 minus 1, 17. So 5 over 17. And this is just us plugging these in and evaluating these pieces of information. So nothing too crazy here. This should be pretty straightforward. This is just the product, sum, difference, and quotient functions all evaluated at those numbers. Okay? All right. Easy money. So on to the next page here, we lose the numbers. It becomes more challenging at this point. And so again, we just have 2 separate functions. The first one's a parabola. The second one is a standard line. And we want to find the sum, difference, product, and quotient function of those functions. Okay? And so this takes a little bit more work and it's a little bit messier, but it's definitely within the realm of what we can do. And so here, this is just going to be f of x plus g of x, again, by definition. And so when we do this, we want to be as careful as possible to actually simplify our terms here, right? And so here it's going to be f of x, which is x squared minus 3x, plus g of x. Oh, I don't have a g of x. I ruined it. I ruined everything. This is g of x right here. Okay? Was the last one like that too? Is everything bad in the world? No, there is peace and happiness. Okay. So I changed that f to a g. I apologize for having ruined that moment. So here's our f of x plus g of x, which is 4x plus 5. And now we want to clean this up if we can, right? And so here I have x squared. We're just combining like terms. Negative 3x plus 4x is just a positive x, and then a 5. So this is our cleaned up composition function in this case. I'll box my answer. Okay. Again, I would pause me and try to evaluate these to the best of your ability. Get through F, G, and H. Stop at I. We'll go through I together. Okay, now that you've resumed me, F minus G is just F of X minus G of X that I have created, which of course is going to be a little bit scary because of the negative, right? So f of x is x squared minus 3x. And, I mean, you should be thinking, this is in parentheses, right? This is our first function. Minus g of x. So g of x is 4x plus 5. So notice here, I've placed my second one in parentheses. You don't really need these first parentheses here. They don't do anything. But this one does. This is going to cause us to distribute this negative in, like this. And so I end up with x squared minus 3x, the first chunk, minus 4x minus 5, right? When I distribute that negative 1 in there. And so my final part here is x squared minus 7x minus 5. This would be my final difference function in this case. And we'll keep going with the same process. Here I have f of x times g of x, again by definition. And f of x is x squared minus 3x, again in parentheses. G of x is 4x plus 5. Oops, sorry. 4x plus 5. And so here it's going to require just a little bit of algebra, right? And this is just a foiling problem. Take this times both. Take this times both. We've done this before, right? And so we get x squared times 4x, that's 4x to the third power. X squared times 5, that's 5x squared. Negative 3x times 4x, negative 12x squared. And negative 3x times 5 is negative 15x. Combine like terms. I get 4x cubed minus 7x squared minus 15x. And that is my product function. Okay, nothing crazy there. And lastly, I have my quotient function. And we're not going to do a whole lot of work here. This is just f of x over g of x. And so in this case, we have x squared minus 3x all over 4x plus 5. And there is work you can technically do here. We're not going to do any of it. Oh, I didn't want to do whatever I just did. Go to my geometry notes, I guess. I want to be back here. We're not going to do any of the work that is showing here. We're just going to leave it like that. So here we have our 4 circled functions, and everything that we want is right here. So part I says give all the domains. And so we're going to list them. So for part E, oh, I'm not on the right thing. Struggling. Part E, looking up at your paper, right? So part E is x squared plus x plus 5. And so what you can really do here is you can look at the domains and ranges, and mostly we're just doing domains, the domains of these two functions, right? If you look at this first function, it's a parabola, and the domain of this is from, I don't know why I wrote it there. Like, what is wrong with me? The domain is from negative infinity to infinity, right? And for 4x plus 5, the domain is negative infinity to infinity. This line. So in this case, when we intersect those two domains, the domains are really nice. There's no restriction here. Everything is really, really beautiful. And so for our first couple, E, F, and G, the domains are just going to be negative infinity to infinity, which checks out with your logic of what a parabola looks like, right? Because as we're looking at this x squared plus x plus 5, that's just a standard quadratic with negative infinity to infinity domain. The same thing is going to be true about part F, because this one's going to be negative infinity to infinity, again a standard parabola, and G, negative infinity to infinity, because this is an x cubed function, right? Nothing there that is scary. Now there is a little bit of fear in part H, and it's nothing crazy, but the idea here is that the same thing exists. It's going to be negative infinity to infinity because the intersection of those two domains is negative infinity to infinity, right? But we can't have the bottom ever be 0. And this, of course, has a denominator that occurs that is 0 when x happens to be negative 5/4. The part in red makes everything sad because, of course, you cannot divide by 0. It's illegal. And so we want to have every number from negative infinity to infinity excluding negative 5/4. So what we're going to do is take the interval from negative infinity up to negative 5/4, and we will go ahead and union that. Okay, again, we want both pieces, right? With the interval from negative 5/4 to infinity. Now we've done this enough at this point that you should know what this means, but that is just every number in the real line excluding negative 5/4. Just throw that part away. Okay? So this is part E through I. Hopefully this all makes sense. Mark anything down or highlight it if you have questions for me. So here is a better picture example. I like this. This is really confusing to a lot of people, and I like that. And so I didn't give us nearly enough room. So I'm going to work over in this section for part J, and then I'll work underneath part K. So I apologize in advance for that. So let's go ahead and just do, how do I want to make this easy to see? I'm going to number this part A, part B, part C, and part D, so you can track what I'm doing, right? And so here's the logic that we're going to use. I'll do the first one, you try the second one, and again, I'm going to do them both. It's a video, but pretend like I'm there, right? I miss you all. Okay, so part A over here is f plus g evaluated at 1, right? And so my top function up here is my g function, and my bottom function is my f function. And so when you're doing this, f plus g of 1 is, of course, f of 1 plus g of 1. F of 1 is my function f at 1. So if I follow f along here all the way to 1, it looks like I'm right there, right? And that is the point 3. My y value is 3. So my f of 1 is 3 plus my g of 1. Again, you're going to follow along until you're at 1. So my g of 1 is 1. So my f plus g of 1 is 4. This is what we're doing pictorially in this graphical representation of what we actually see. It's a little bit tricky, but we can do this. Part B, f minus g of 0. F of 0, and I'm not going to trace the picture anymore, but f of 0 is 0, minus g of 0 is, f of 0 is not 0. I'm a complete and utter liar. F of 0 is 4, g of 0 is 0, and 4 minus 0 is 4. For part C, f times g of negative 1, so f of negative 1 is 3 times g of negative 1. I can't. Sitting in my office doing this is so confusing to myself. I'm looking at the wrong picture every single time. Let's trace it again. Here's f right here. F of negative 1 is right here. So that's 3. Is that what I said the first time? Probably is. Times g. Here's the g1 of negative 1. That's going to be 1. So I have 3 times 1. That is, of course, 3. And part D. And I'm sure you're all being very reasonable about me messing up once. You're going to scream at me on Tuesday. It's okay. Okay, D is f divided by g of negative 2. So we're going to negative 2 in this case. So f of negative 2. Negative 2 is over here. I can't whistle, by the way. That's 0. Divided by g of negative 2. Oh, no. Did I do it again? No, I didn't. G of negative 2, which is 2. And, of course, 0 divided by 2 is just 0. So I train wrecked this trying to look at my screen and my iPad at the same time, but you get the idea, right? Look at the, and I wish they were different colors, right? Look at the f function to get your f value. Look at the g function to get your g value. That would help if I would have just done that to start with, but here we are in this nightmare, and I'm not redoing this video, so here we are. Okay, for part K, the same exact thing is going to happen. It's much easier on this side because the numbers are right there in front of you, right? Because as you look at this table, right, this is your x value. This is your function evaluated at this x value, right? So negative 5 is just f of negative 2. That's the idea here. 0 is just g of negative 2. And so as I do this, right, maybe pause me at this point, try this one, and then resume me. Okay, I'm resumed. F plus g of 1, I'm looking at the 1 section, that's right here, right? F plus g of 1, so f of 1 is 1, g of 1 is 6, 1 plus 6 is 7. That's the logic that we're going to do here. And then I'll erase that piece because of technology. B, we have f minus g of 0, so now we're looking at this row. F of 0 is negative 1 minus g of 0 is 4. That's negative 5. C, f times g of negative 1. So I need to move this over to the negative 1 section. Boop. F of negative 1 is negative 3 times g of negative 1 is 2. That's negative 6. So far, so good. And the last one is going to be f over g of negative 2. So f of negative 2 is negative 5 over g of negative 2 is 0, which is, of course, undefined, right? Cannot divide by 0. That one went way better than the first one did. Okay, so this is just a representation of what is actually happening. Okay, so here is one more of these, and we're getting a little bit more complicated, but I want the exact same pieces, the A, B, C, and D from the previous page. So you might need to go back and look. I'm not going to because I'm lazy and I have it in front of me on a screen, but this is f of 1 plus g of 1. That's the first one. So f of 1 plus g of 1. Now f of 1 in this case is just 7. G of 1 is negative absolute value of 1, right? So that is going to be negative 1. So this is 6. Now, again, this is the A, B, and C, D from the previous page. B, that was f of 0 minus g of 0. F of 0 minus g of 0. So this is going to be 4 minus 0, which is, of course, 4. C, from previous page, was f of negative 1 times g of negative 1, which is f of negative 1 is 1. G of negative 1 is negative 1, so 1 times a negative 1 is a negative 1. And D is f of negative 2 over g of negative 2, right? And so f of negative 2 is negative 2. G of negative 2 is negative 2, so this is a positive 1 for a solution. Again, this is much easier, right? The first one is the only complicated one. Okay, moving on. We get into the smallest amount of calculus of all time, just baby calculus. This is called the difference quotient. And the difference quotient is this beautiful measure of the average rate of change of a function over an interval. So what we're actually doing is we are computing the slope of what is called the secant line through 2 points on the graph of a function. So our idea here is we have a point here, right? That's x comma f of x, that's our first point, and a point here. And so we're going to go ahead, and then the difference between this point here and this point here is some h value, right? This is some h value right here, and the same thing here. That's some h value, right? And it's actually this one that you start with. This is the h value, and this is the gap that is decided by this h value over here, right? And so this equation that I'm going to highlight in purple right here. Oh, that looks bad. Hold on. I think if I just do 2 strokes like this, yeah, it looks better. That is our difference quotient. That is the slope of that red line, or the secant line, through those 2 points. And as we start to take more and more of these difference quotients, we build something that is called the derivative in calculus. And it's really, really cool. But this is just the baby version. But it's a very good example of showing composition of functions or working with functions in this way. Because in here, you'll see we have this x plus h chunk. And working with that is a little bit different. And so we'll do an example or two of this. And it's really, really, really messy. But it's kind of cool how it works out. So let's do an example here. We're looking at the function 3x squared minus 2x plus 4. And we want to evaluate the difference quotient of this. And so again, our formula is right up here. I'm not going to keep it on the screen, but it's right here. We're going to use this formula straight up. No changes. Okay? And so our first chunk of that formula is f of x plus h. So I'm going to take my function x, f of x, and I'm going to plug in x plus h everywhere I see x. So I have 3 x plus h minus, or squared, excuse me, minus 2 x plus h plus 4. Right? That is my function that I start with f of x plus h plugged in. Okay? Then I want to subtract, right? The next chunk is minus f of x. So I'm going to subtract and put big parentheses because I need to put my function in here. My original function, 3x squared minus 2x plus 4. Close it. Big division symbol. On the bottom, it's just h. So the cool part about difference quotient problems is that it's a lot of algebra. It's really, really messy, but if you keep track of everything, most of the h's are going to cancel, which is kind of cool. Okay? And so the really challenging part is just the first part, right? We need to distribute this x plus h squared. Maybe on the side it's worth doing this. Here's x plus h times x plus h. That's x plus h squared. So this turns out to be x squared plus xh over here plus xh again plus h squared. right? And so here we're going to end up with x squared plus 2xh plus h squared. So that's a little bit of side work, a little bit of foiling, right? This is for us just to keep track of. We don't have to tell anybody we did this, right? This is a secret. But this is something that you can look at and use here. So that's just this chunk right here. And so in here we have 3 times that whole chunk, right? And so we're going to end up with 3x squared plus 6xh plus 3h squared. That's our very first chunk. Did I miss anything? Plus 3h squared minus, now we have this chunk right here, 2 times x plus h, so 2x minus 2h plus our 4, don't forget the 4 chunk, and then distribute that negative in there. So we have negative 3x squared plus 2x minus 4 all over h. Now, I'm a little nervous, right, because I've been having a rough video as far as my success goes, but this is something that you're seeing me being a little bit careful with because there's so many opportunities to mess up that it's really, really obnoxious. And my advice to you is if you're doing this problem and you don't end up getting something that you expect, I would start over. It's very hard to find your mistake. But what you're going to see in this is that we're going to get a bunch of things that cancel, right? We have a positive 3x squared that cancels with our negative 3x squared. We have a negative 2x that cancels with our positive 2x. We have a positive 4 that cancels with our negative 4. Okay? And so when we cancel all that stuff, we're left with 6xh plus 3h squared minus 2h. And the bottom, we still have our h. And now there is an h in every single term, so we can cancel one h. And we end up with 6x plus 3h minus 2, which is our difference quotient. That is the slope of the secant line. As you change that h value, that is your slope. 6x plus 3h minus 2. Okay? Lots of fun. Really enjoy those problems. It's a lot of work. So make sure you practice these, the ones in your homework. Make sure you do them. This is worth doing, I promise you. Okay? And our last couple pages here are going to be on actual composition. So we have not got to composition yet. That was the compose part. And so what composition is if you think of those Russian dolls, right, where it's a big egg-shaped doll, sort of, and then you open it, and inside that doll there's a smaller doll. And you open that, and inside that doll there's a smaller doll. And that's the idea of the composition of functions. It's just functions inside of functions. So here it says, if f and g are functions, then the composite function, or composition of f and g, is defined, and the way you read this is f of g, that little open circle, f of g of x. And this notation over here means the exact same thing. That is the exact same function as the left side, but to me, it is incredibly much easier to understand. Because what you see here is you see this g of x function right here is actually inside f of x, right? It's inside the parentheses of f of x. And that is what this notation is trying to get at, is that f of g of x is g of x plugged into f of x. And that's the whole idea behind it. The domain of the composition is the set of all numbers in the domain such that g of x is actually in the set of all numbers in the domain of g, where the output of g of x is actually in the domain of f. And so for now, we're going to just look at the functions and practice with them a little bit, and we can talk further about the domain. Okay? So here we have f and g. F of x is the square root of x plus 4, and g of x is 2 over x. And so we want to find f of g evaluated at 2. And so this is just, and again, I'm going to rewrite using the other notation because I find it really helps. But this is going to be f of g of 2. So it's going to be g of 2 plugged in here. And so the logic that we can do is we're going to work on the side over here. G of 2 is just 2 over 2, which is 1. So we bring this logic back over here. This is going to be f of, and now we just said that g of 2 is 1. So I'm going to put a 1 in here. And f of 1 is the function of f with 1 plugged in. So the square root of 1 plus 4, which is the square root of 5. This is our f of g of 2. And on the bottom, this is going to be g of f of 5. Try this one on your own. Pause me. Okay. F of 5 is the square root of 9. And of course, the square root of 9 is 3. So this is going to be g of 3. And g of 3 is just the g function with 3 plugged in, so 2/3. So nothing too crazy here, right? Again, you're thinking of those nested dolls, okay? And so here, we're going to give a little bit of work. And so we're going to work with f and g. F is square root of x minus 1, g is 2x plus 5. So for the first one, we want to find f of g. And again, this is the same thing, just no numbers. So f of g of x. Again, I'm reading using other notation. You can just use this notation if you want to. That doesn't bother me or anything. I've just found the other ones easier for students to understand. So this is our f function with g plugged in. So our f function looks like this. But I took out x, and we're going to replace x with our g function, which is just 2x plus 5, like that. And so now you can simplify a little bit. This is going to be 2x plus 4. And that is our actual function. So now when you look at this function, what you can do is you can just take the domain of this function, of course, right? The domain of this function is from -2 up to infinity. And we know how to do this based on the parent function, right? If you actually did a little bit more work here, and you said this is the square root of 2, and then you factor that out, that 2, and you got x plus 2, right? You would see that this is a function that has been moved left 2. Right? Or you can look at the inside of the function and say, when is this going to be negative? Right? This is bad if it's negative. And you solve this. 2x is less than -4. X is less than -2. All that stuff is bad. Right? A couple ways to look at this. Now, if we look back at the previous idea, where it says the domain of the composition is the set of all values that are x, where the domain of the inside function gives you an outside domain that is actually in the domain of the outside. Now, it's a little bit confusing, but if you look here, we're looking at all the values that give you a domain where in f, you get something that is in the domain of f of x. And so if we look right here, the domain of this function is from 1 to infinity. So we're looking for all the x values for g, that when I plug them into g, I end up getting a value that is in 1 to infinity. I find it's easier just to calculate it like this, but there are times when it's useful to use the logic. But we know how this function right here works, and we can just find the domain of that. Okay? I showed you 2 different ways. Q, part Q, is just flipping it, right? G of f of x. So it's going to be your g function, which is 2, so g of f of x is going to be g of x, which is 2 parentheses plus 5. But now we're going to, instead of writing x, we're going to plug in f, which is going to be root x minus 1. So of course this is just 2 root x minus 1 plus 5, which is a little bit nicer of a function, right? This is your square root function, your parent function, that is stretched by a vertical factor of 2 and moved up 5 and over 1. So our domain here, as we know, right, is going to be from 1 over to infinity, because we've moved our parent function, and this is a good reminder that if you don't know your parent function domain, it's time to study those parent functions from 2.6. We've moved our parent function over 1, and we end up with this 1 to infinity domain. Okay? All right. Last page? Not bad, not bad. Okay, so here's another function. F of x is 5 over x plus 4. G of x is 2 over x. We're going to do the exact same work here. Gets a little bit more messy, but not too bad. Okay, so f of g of x. So again, this is outside function with g plugged in. So my f function is 5 over, we don't put x, plus 4. And then g of x is, of course, 2 over x. That goes right in there. And so there's a little bit of work we can do here. We can clean this up simply by multiplying the top and the bottom of our function by x, which we're allowed to do because that's the same thing as multiplying by 1. And so on top, I get 5x. On the bottom, the x's cancel at first, so I get 2, and then I get plus 4x. So that's a little bit cleaner function. Okay? And so this is somewhat messy, and this is where it actually comes into play. And the reason is that I know, based on this information right here, that there's a number that I already have to exclude. I know x cannot be the value 0. Because g is my inside function. G is inside of f of x. And so my x values are going to go into g first. And I know that I'm not allowed to plug 0 into g. And so 0 cannot be in my final domain. And now when I look at this function over here, if I look at our final function in the bottom, if I set 2 plus 4x equal to 0, and I solve this, I get a negative 1/2. So I also know that I'm not allowed to have negative 1/2 in my domain. And so my actual domain here is going to be all values of x except for negative 1/2 and 0. And so that's going to be negative infinity up to negative 1/2, union with negative 1/2 up to 0, union with 0 up to infinity. And that again is just every real number cutting out negative 1/2 and cutting out 0. Okay? And that comes from our purple highlighted portion and then our final portion where the bottom can't be 0. Now this part right here isn't going to influence us here because we're not actually plugging in numbers into here. We're plugging in numbers into here that end up in here. That's the idea. And now we flip it. Here's g of f of x. So g of f of x is your g function with f plugged in. Your g function is 2 over x, but x is 5 over x plus 4. A little messy. So we can clean this up just a little bit. Now, if you've ever seen division by a fraction, that's the same thing as taking 2 and multiplying by the reciprocal, right? Dividing by a fraction is the same thing as multiplying by its reciprocal. So this is going to be the same thing as 2 times x plus 4 over 5, which is going to be 2x plus 8 over 5, which is actually a fairly beautiful formula, right? This is 2/5 x plus, oh, I don't write pluses anymore. My hand's cramping. Plus 8/5. 2/5 x plus 8/5. That's a y equals mx plus b equation, right? And so that's going to have a beautiful domain. Well, actually not so nice, because there's one value that we need to immediately cut out. And that value is going to occur right here. See how the f of x's are inside? And we know that f of x cannot have a value of negative 4. So it's worth tracking that early. We know that x cannot equal negative 4 because that is our inside domain. And so just because this is a gorgeous line over here that has a perfect domain of negative infinity to infinity, we still need to remember not to choose negative 4 because our inside would be undefined. So it's going to be every number except for negative 4. So negative infinity up to negative 4, union with negative 4 up to infinity. We've cut out negative 4 from the options here. Okay, 2 more. You're almost done. Hang on. Take a deep breath if you haven't breathed yet. I don't know if I have. So here we're just looking at this this little equation. We want to prove that, you know, this thing is not reversible. F of g is not the same thing as g of f. So we're going to do that by an example. Of course, in math, if we can show a counterexample, that's enough to prove that it's false. And so we're going to check both f of g and we're going to check g of f. And we're going to see if we get the same thing. Okay? Not too much work here or anything. But f of g is going to be 2, 3x squared plus x minus 5. This is just f with g plugged into it. And if I evaluate this a little bit further until I'm convinced this is 6x squared plus 2x minus 5, that's our final form. Now for the g of f part, this is going to be 3, 2x minus 5 squared plus 2x minus 5. A little bit messier. Actually, I'm going to move myself up a little bit. It's a little bit messier. Okay, on the left side here, I'm going to do 2x minus 5 squared just so you can see it. If we were in person, I would just say do it, but we can go ahead and show it. So 2x times both, that's 4x squared minus 10x, and then negative 5 times both, so negative 10x plus 25. So this first chunk is 3 times 4x squared minus 20x plus 25, and then plus my 2x minus 5 at the end. So this is 12x squared minus 60x plus 75 plus 2x minus 5. And then we can clean everything up and get 12x squared minus 58x plus 70. Which, of course, is obnoxious, right? Super, super not clean. But are these things the same? Absolutely not, right? These are not the same. So we have just shown that f of g of x is not the same thing as g of f of x. Those are different, okay? We're not sure why yet or how, but we know they're different, okay? And our last one, I love these, right? We're ending on a nice, easy one. This just takes a little bit of different thinking. And for some students, you're sitting there thinking, this is really, really easy. And for some of you, this is a little bit more challenging. But we just want to find two functions, f and g, and we're just going to dream them up, right? F of x is equal to something, g of x is equal to something. Where we want the composition function, f of g of x, to equal all that stuff. So, for what it's worth, pause me. Try to write down f and g. Okay, you've resumed me. I even took a little pause there. I fell asleep for a second. So my inside function and outside function is the way I look at this, right? I like to look at, there's an inside function plugged in, and there's an outside function that's kind of eating everything else, right? My inside function in this case, which is going to be g, because of course my notation that I like to use is f of g of x. So g's on the inside. My g of x is going to be 3x plus 2. That's the chunk that's plugged into the inside. My chunk on the outside, my f of x, is going to be 4x squared minus 5x minus 8. Because you see, if I mentally ignore these highlighted chunks, you'll see that it is 4x squared, that's my highlighted chunk, minus 5x minus 8. And if you actually plugged in this g of x piece into the f of x piece, you would get what is written. And that's the end of 2.8. So you have an online homework on Math Excel. Do that first, please. And there's some notes to Miss Bondi, and she knows all this. After you've done that, try to go ahead and do the paper homework. And I will see you on Tuesday. Current plan is that we'll go over this and review it, and then we will take a test at some point. So do as much of this as you can. If you have any questions, let me know. Have a wonderful weekend. I'll see you on Tuesday.